Welcome to Logical Verification 2020-21. This video is about Chapter 11, Sections 5 and 6, Subtypes and Quotients. In the preceding section of the chapter, we have looked at Lean's foundations, at universes, and the axiom of choice. In the remaining two chapters, we will now look at something more exciting and constructive, namely about two new constructions, subtypes and quotients, that allow us to make new types out of old ones. Okay, so let's say we have, can't draw. So let's say we have a type, let's call this alpha. And let's say it has some 16 elements. Okay. So let's imagine we have a type with 16 elements that we have here. So, with a few elements, maybe not 16. Maybe let's make this a bit smaller. Okay, so then we'll look at two different constructions now. So the first one is called a subtype. So what does a subtype do? It takes a look at some subset of the elements. So let's say all the elements that satisfy the predicate P. So we have a predicate P which goes from alpha to prop, and P is true of some of those elements. And then the subtype, well, so let's write this using the nice syntax. The subtype of all x in alpha, such that P of x is true. The subtype now consists of exactly those four elements. So this is the subtype. Another way to write this is as subtype alpha P. Okay, so these are the same thing. So, so if we have a type and we only want to look at some of its elements, maybe think of alpha maybe as lists and the P of lists of length 2 or something. Alright, so if you want to only consider some element with a given property, then we get a new type, namely the subtype of elements satisfying this property. Okay, so this is one way in which we can construct a new type using the subtype construction. And another interesting one is the quotient construction. And what we get here is a different type. So the quotient construction doesn't depend on the predicate, but instead it depends on an equivalence relation. So if we know that some of these dots here are equivalent, such as, let's say, this one here is equivalent to this one, and this one here is equivalent to this one, and this one here is equivalent to this one, so let's say we have an equivalence relation that tells us that some of these dots are equivalent. Then the quotient construction turns each of those equivalence classes, those subsets of the type that are where all the elements are equal to each other, into, well, it identifies them and makes them into one element. So we get a new type that kind of looks like, that has 4 elements, one for each of those equivalence classes here. So this is the, well, let's call it the quotient of, oh, well, so in Lean the syntax is a bit more complicated, as we'll see, but let's just abuse this notation for a bit and just write this one here. Well, maybe let's just write quotient by this equivalence relation. Lean syntax will be a bit more complicated. But the general picture is that we will now look at these two ways to construct new types from old ones. One by only looking at a subset of the elements and forgetting the rest. And the other one, the quotients, by identifying elements. Both of them are very useful. So if, for example, subtypes can be used to consider, restrict yourself to well-formed objects. For example, if you consider binary trees, you can then consider the subtype of well-balanced binary trees or full binary trees, or whatever nice properties you want to have. So you can make certified data structures that have their invariants built into the property of the subtype. And quotients are interesting when you want to, when you have a certain representation of your type. For example, if you want to represent a finite set as a list, then you can take a quotient which ignores the order in the list. So a quotient allows you to treat two seemingly different objects as the same one by explaining to Lean which element should be equal. And both of those constructions also appear in mathematics, very importantly. So as we'll see throughout the rest of this course, many important fundamental objects in mathematics, like the integers, the rational numbers, the real numbers, and then the p-adics, all of them can be obtained using, are obtained using these operations. Okay, so let us look now at how the Lean syntax looks for these objects. So let us start with the subtypes. So as you've already seen on my drawing, the subtype syntax in Lean is written by using these curly braces, and then you write variable of type, 2 slashes, and then the property that should be true of this variable. So for example, as we have here, we have the type of all I in net such that I is less or equal than n. So this is just the syntax. And in Lean, this syntax notation is defined as the subtype. So this is just syntactical sugar for writing subtype of type and the predicate. And the subtype type itself in Lean is nothing special. You can define this yourself. Well, you could define it yourself, but then the notation wouldn't work. But it is really just a structure of subtype, which has this carrier type here, and then the predicate on the old type. And then it has two fields. One is the element, and the other one is a proof that the element satisfies this property. This is exactly how a subtype is implemented in Lean. As you can see here, it's a subtype it's a structure with these two fields here. Okay? So these subtypes are really just structures that combine an element of your type with the proof that the desired property is true. In chapter 5, we looked at binary trees, and we defined what it means to be a full binary tree. And now we can define the subtype of full binary trees, that is, binary trees that are full. Okay, this gives us a new type, and now we'll take a look a bit at how we actually work with subtypes. So maybe the most important thing that we want to do first is how do we create elements of a subtype. We do this using the subtype.make constructor. Remember, this is just a structure. It takes 2 arguments for each of the fields. First, the element in the original type, and then a proof of that the property holds of this element. So it takes here this element, and then it takes a proof that the property is true of this element. Okay, so let us create a very simple full binary tree, namely the empty one. And this works as we expect. We take subtype make, and then give it as an argument the empty binary tree and the proof that the empty binary tree is full. If you think back a few videos, at the beginning of this lecture, I told you that proof irrelevance will come in handy for subtypes. And let me now show what I meant back then. So the idea is that this empty full binary tree, we've put here a certain proof in here that the empty binary tree is full. And the nice thing about proof irrelevance is that it does not matter in any way whatsoever what proof you put in there. So if we want to prove that the empty full binary tree is the same as the subtype consisting of, so the element of the subtype consisting of the empty binary tree with any proof of its emptiness whatsoever, so that the empty binary tree is full. Okay, so we've defined the empty full binary tree as the element of the subtype consisting of the empty binary tree together with the proof is full dot empty. Okay, and using proof irrelevance, I've already defined this one, so let's use full prime. Okay, and the nice thing about proof irrelevance is that it does not matter which proof we choose at all. The empty full binary tree is equal to the same construction with any proof of the fullness of the empty binary tree whatsoever. And we do not need to use any to reason about proofs. We do not need to keep a whole theory of when 2 proofs are the same. Using proof irrelevance, these are just always the same without us having to do any work whatsoever. Okay, so now we know how to create elements in the subtype. And well, we can also create more complicated things. So if we use subtype make with a more complicated argument, we then need to provide proof that this more complicated argument is full. Okay, well, you know how to do this. And then we can reduce this full binary tree. So if we reduce the value, so full binary tree is, as I've said, it's a structure with 2 elements, and we can look at both the value as well as the property, so that this value satisfies. And if we reduce the value, we see that indeed we get back the first thing we passed to the constructor, and if we look at the property field, then we will see that we get a proof that the value satisfies it, the is full predicate. Okay, so now that we have this subtype.val function and the subtype.property function and the subtype.make constructor, we can lift functions on binary trees to full binary trees, as long as they preserve the is full predicate. So we've proven that the mirror operation in binary trees preserves fullness, and hence we can lift this operation to full binary trees. So if we maybe look at it this way, so what we had is a mirror operation, and the mirror operation had this property that whenever we have an element in this full subset, then it maps to something in a full subset. So maybe it does this, and then it does this, and maybe it maps this to itself. But we never get outside of this subset P. And then we can just consider this mirror operation as an operation on the subtype. Okay, so now we have defined an operation on this subtype, which gives us an interesting problem. That now we want to prove things about equality on subtypes. So we want to prove that that if we do a mirror operation twice on the full B-tree type, then this is identical. Then it gives back the original full B-tree. And for this, we need to show that this equality of the element, so this is an equality between elements in a subtype. And for this, we use a nice lemma called subtype.eq, which tells us that two elements in a subtype are equal if their values are equal. Okay, and once we have this, we can just use the simplifier to push the val inside, replace full b-tree.mirror by the mirror operation on the underlying type, and then we have a simple property of the underlying type. And this is a general pattern that we often see when you lift operations to subtypes. You typically then always want to, when you have an equality between subtypes, you always want to look at the equality of the values using the subtype.eq lemma. Okay, so this was one of the ways in which you can construct. So now we've seen how to construct subtypes. And next we're going to look at how to do quotients in the next video.